All right, so in this lecture, we got two more examples of the work energy principle, work energy analysis technique being applied to rigid bodies in planar motion. And we'll just jump into this first one. So this is another torsional spring. We saw one last time. Another torsional spring, and all this system really is, oops, I'm kind of zoomed in far into this problem here because I knew the words are pretty small. But we wind it up, right, and that stores potential energy into the torsional spring, and then that moment then responds by, well, with the the bar here. Well, this is like a negligibly masked bar. This is just bars here to make it so that this will cause a motion. Well, I forget which direction this is being pinned up here, but this will then produce a translational motion of the big disk, and it rolls without slipping. Okay, so let's analyze this. We're looking for what that speed is. Let's see, what do we determine? The maximum speed reached by the center of the disk, so the center of mass there. Okay, so let me zoom back out slightly. So we got the full page in there. Even more. Yeah, I think I printed this one a little bit too small. Okay. And I'll remind you of some of those properties as we get along here, that are, or some of the given information. So let's draw a free body diagram, right? Okay, so this is now just at any point in the unraveling. There's 2, 4. Okay. There's our center of mass G. We have a weight pulling down. There is a moment from the torsional spring, and there is a normal force. And right, there could be friction too. But as we've said, rolling friction does no work. So that's the moment that would then want it to roll that way. Yeah, so this is going to move this other way. And so the friction force would be there. Okay. All right, let's jump in. Those are all the forces. Now let's take a look at or start analyzing our work energy. Okay. Work energy says take kinetic energy at 1, potential energy at state 1. We've got, this needs to be a plus. Plus our work that doesn't go anywhere else, so it's non-conservative work, plus anything else. And then we got kinetic energy, potential energy on the other side in state 2. So our state 2 is going to, so state 1 is going to be right before we release it. Okay, and so that means that there's no motion. Okay, released from rest. And what else? We can also throw out this term. Now this term, you might say, well, there's a moment there, right? Don't we got to put that? Nope, this is a torsion spring, so we'll include that in the potential energy. You might also say there's friction, right? Isn't that non-conservative work? Nope, right? Friction does no work. We talked about this last time. So rolling friction does no work. And again, the reason is that contact point there in which the friction is being applied, that point only moves upward. And so the dr associated with that term, so F dot dr equals 0. That force is horizontally, the dr is upward. There's no, the dot product would then be 0 between the two. Okay, so that's 0. And then also, well, I think we mentioned this already, the moment, we can put it. Right, moment from torsional spring included in potential energy terms. Okay, so I think those are all the important notes to ourselves. Now, one thing about the potential energy, they're not 0. Oops, wrong color here. They're not 0, but the gravity isn't going to become important because this just now rolls on a horizontal surface. So we don't need to worry about the gravitational potential energy. Height never changes, at least of our center of mass. Okay, so that's something to be said about our potential energy terms. So having said all that, what terms are left over? Well, in potential energy, we have the torsional spring, 1/2 k theta 1 squared. And that's it, okay? And then on the right-hand side, our kinetic energy, well, we got 1/2 mv2 squared. That's what we're looking to solve for, is that speed, plus rotational, 1/2 I omega 2 squared, okay, plus 1/2 k theta 2 squared. So here's our, let's make sure we know where these all come from. There's our potential energy, there's our potential energy, and then these two terms are our kinetic energy. All right. So let's take a look at this. What can we say? Okay, so first of all, theta 1, that's how we winded it up. And here it said 3 rotations. Okay, so 3 rotations is 6 pi, right? Each rotation is 1 pi. So theta 1 equals 6 pi. That is 3 rotations. K is given in the problem statement, so we know everything here. Look here, mass is given in the problem statement, so we know that. Our moment of inertia here. So, and then this is like what we're looking to solve for. Okay, so that's good. Obviously, we're not looking to plug a number in, otherwise we'd be done with the problem. Our moment of inertia about the about our center of mass for our circular disk is 1/2 mr squared, and we know everything there. Omega 2, right? We saw this in a previous example as well. Well, this is just a rolling disk, right? Rolling planar motion here. So V2 is just R omega 2 is the relationship between translational velocity of the center and the rotation of the disk. And so, right, you can see that here, right? This is a fixed point. If this is rotating with omega at any time, then the velocity here has to is a you know, if you work through the relationships, which we've done many times here, the velocity of the center of the mass with this fixed point, you know, instantaneously a fixed point here, is the radius multiplied by omega. So there's the radius r. Okay. So we got V2, that's the velocity of the center of mass, is omega 2, or, right, omega 2 is then, could be replaced with V2 over r. All right. And that's what we'll use. And then, now if we look at this, right, what the question asks for is what's the max speed? So let me start by writing what we have here in terms of, you know, just kind of rewriting it, but plugging some of the things in, but not everything. So we'll wait to plug in 6 pi until we get there. Here we have, both of these terms have, well, we have a 1/2 mv2 squared, that's what we're looking for, and then this term here is a 1/2 mr squared v2 over r squared. Okay, now the question is well, what is theta 2? Okay, and this is where the max, the problem statement says, like, what determined the maximum speed reached by the center of the disk. So in what ways can we maximize theta? Well, this is a term that's going to be added on here, okay? Added on to the right-hand side. So when we go to solve for V2, it's going to be subtracted from the other side, and it's definitely positive because it's a squared quantity. So how to maximize something that can only have a negative contribution to the thing you're trying to maximize is to make it 0. Okay, so our max speed occurs when theta 2 equals 0. So this also, that means that we've now gone from pure potential energy to pure kinetic energy. So we have no, we're not storing any more potential energy in the torsional spring. It's all gone to kinetic energy. All potential energy goes into kinetic energy. Okay, and that's why we have nothing over there, right? Let's now solve this, right? 1/2 on every term. So we have k theta 1 squared equals mv2 squared 1 plus 1/2. A lot like what we had last time, and that's because the radius squared cancels. So we have v2 equals, this is 3/2, pull to the other side, that's 2/3, 2k theta 1 squared over 3, divide by the mass before we square root. Okay, this is a lot like I guess a lot of these relations are a lot like that other example we had last time. Actually, a much simpler ending relationship, though. Okay, K is given in the problem statement as 4 times 10 to the negative 4th Newton meter per radian. 6 pi rad, that is squared, for theta 1, 3 over 0.1 kilogram. Plug all that in, we get a max velocity of 0.9734 meter per second. Okay, another practice of a torsional spring. All right, so good one to start with. Okay, we got one more example problem to go. Okay, so here's the last example here. Now, we have, so this is definitely, I think, of the examples we looked at, the most complicated setup here. So we have 3 individual components that are connected together, right? So we have the slider sliding down, that's slider A, all right? It has, the mass is given, and then it's connected to a circular disc through this slender bar. So a slender bar, circular disc, and a slider here. And the 2 kilogram slider, and then the bar and the disc are both 4 kilograms. Okay, so that's good. And then what we're saying is now the system is released, so this is going to slide down. At that time, right, then the disc had better kind of roll outward. And we want to analyze, actually we want the angular velocity when theta reaches 0, so when it's coming to this orientation. So let's put that orientation in there, right? So this is going to drop until we get to, well, let's do it this way. Okay, that position there is definitely not going to, that vertical position is definitely not going to change. So at some point, we will have the disk moving up to there, and at that point, this slider A should be in this orientation. Okay, and it is right moving downward with some velocity of A. And let's see. Now we use our intuition here. Think about like this system, right? This slider falls, and right at this instant when theta has reached 0. By the way, let's label these states. So the state you see like in the diagram is state 1, and then this would be state 2. And then the bar is connecting them in between. So as it slides down, the wheel is going to go outward, and then right there it's turning to go back inward, right? So it's here, slides out, and then rebounds back. So right at this time, if we think about it, we might have a good idea what to expect for the potential, velocity of B assumed in the positive x direction, or the positive coordinate direction here. Maybe there's a positive omega here of B assumed in that direction. We'll see it come up, but you could have some idea of what these two values are going to be going into the problem. But we'll keep them in there without assuming values for them, and we'll see what that does. Okay, let's label a few other things here on the actual diagram before we go into our free body diagram. Let's see. I think the center of masses are pretty obvious for A and B, but we need one for the bar, which is right about there. And what we're actually looking to solve for is what is the omega of the bar, the angular velocity of that bar at the particular instant of state 2 as we've drawn it, right? And so the velocity of the bar maybe at any given state is something, maybe has some components in the 2 different directions there. I tried to draw it a little bit off vertical. It's definitely going downward, but it's also going out in this position. But just making some observations here. Let's see. We have to pick a datum level, and obviously these positions for that, the center of mass of A is also going to become important, right? In fact, this is going to be the position of A at position 1. This will be the position of the bar at state 1. Okay, and let's make this. I don't have much space. I'll label it right here. So this will be our datum. Okay, and so that means that YB always, right, equals, and it's also Y2 for all of them, right? You see how at the second state they all come to there, that's all going to be 0. So that's a good choice for datum, because in the final state the gravitational potential energy for the entire system is then 0. Okay, let's get going here. I think also in the problem I'm going to refer to this as length L, or maybe just do capital L, because that's what it shows up in the moment of inertia calculation or formulas. That at least what I use. Okay, let's go to our free body diagrams. Right, so we'll draw a free body diagram for each of these 3 different components. So free body diagrams, and let's start here with the slider at A. Okay, so here's A. Let's put its the center of mass kind of right in the center. Let's see. So it'll have all of the forces, right? So it has a weight. And let me rewrite this as MAG. Okay, and then it's also, based on where it is in its slide, is going to have a force from the bar, assuming the bar is like in tension, let's say, right? So this is the force of the bar onto A. So I'll represent it as force of bar onto A. And that's it. Okay, no, there could also be a normal force. There's no friction here. Neglect the friction force in the slider, so we're not even going to put that in here. But there could be a normal force, which would look something like... we'll just sneak it in there on the side. All right. Now, this is a different free body diagram, but I kind of want to orient it as much as possible. We'll put the bar right in line with that force, so that when we put in the force felt by the bar, this is going to be the force of A. I think the notation is actually backwards. So this is actually the force of the bar on A, and this is actually the force of, so it's the force of A on the bar, this is the force of the bar on A. The A needs to be in front. I think that was the notation we had earlier, so A bar. Okay? Well then, there'll also be a force felt on the other side, that's down to B. Force on the bar due to B. And then at the center of mass, for the slender bar, there is the mass of the bar times gravity. Great. Okay, and then the last one down here, we have our circular disk, center of mass right in the center. It has a mass of B times G, also has a normal force acting upward. This one could have it has to have a friction because it's sliding. So let's put the friction at that point. And then, and then we have, this is the force on B due to the bar. Okay, those are all the forces, and there's a lot of them. But again, when the situation is tricky, always good to relate. If we're looking to relate velocities to heights, well, this is a velocity. Go to work energy. Sometimes things get much easier. Okay, so this says is kinetic energy at 1 plus the potential energy at 1 plus any other work that we haven't considered in any other term equals kinetic energy at 2 plus potential energy at 2. Okay, so remember, 1 is the state we have it here, which starts at rest. So this is 0. It's at rest in state 1. This term, potential energy 2, I already talked about this, right? This is because state 2 is when the theta has dropped to 0, the datum is set to the y2 level. Smartly, I was just realizing I was off the page. Sorry about that. Okay, so work energy written out, kinetic energy at 1 is 0 because we're at rest. Potential energy at 2 is set to 0 because that's where we smartly chose where the datum was. Kinetic energy at 2 is definitely not 0. Where do we have kinetic energy? We actually have quite a bit, right? Everything's moving. This is moving. The bar is moving and rotating. A is not rotating, but the bar is moving and rotating. The wheel, the disc could be moving and also could be rotating. And we're going to keep all those. Potential energy at 1, right? The bar and the slider have potential energy, but there's no spring or anything. talk about this one, right? Let's think, right? So slider friction is ignored from the problem statement. There's no applied moments to be added here. Okay, but you might say, well, there's the friction due to, you know, on the disk. Well, again, the rolling friction does no work. Okay, as we've seen before, again, it's the fact that the force is in the normal direction to the change in direction of that point, which would go upward for a rolling motion. So, yeah, this is 0. There's no work that we're missing out in terms of other than the potential energy kinetic energy. So what we have here is pure potential energy moving into kinetic energy, but kinetic energy in many different forms. So we need to be careful when we write them all out, right? So anything on the left is going to be potential energy at the start. Anything on the right is going to be kinetic energy at the final state. So we have potential energy due to the slider A at the YA1 position, and we have the bar and its Y position at initial, Y bar 1. Those are the potential energies. The wheel, or the disk, is at the datum level. So that doesn't change its potential energy. Okay, kinetic energy. Okay, so slider A is only translating downward. Okay, so it only has a kinetic energy of 1/2 mass of A VA squared. This is kinetic energy of A2 at the 2 state. Okay, now let's go to the bar. The bar, again, is when we get to this state here, is moving downward and rotating, right? So we need to have the full, both terms. Translational kinetic energy, that would be 1/2 mass of bar times its velocity or speed squared, plus rotational. That's going to be the moment of inertia assumed to be about its center of mass, omega for the bar squared. Okay, these two combined is the kinetic energy of the bar at state 2. Okay, and then we've got similar terms for the wheel, right? In general, it could be rolling and translating, which is what disks tend to do. So this has 1/2 m of b vb squared plus 1/2 I about its center of mass omega b squared. And this is the kinetic energy of b at state 2, time 2. Okay, so it looks like we're close, but if we look at this, we definitely from geometry alone could determine everything on the left hand side, but we have VA is an unknown, we have V bar unknown, omega bar, VB, omega B. I mean, there's 5 unknowns hidden here, right? All of these velocities, both rotational and translational. So we got to do some kinematics to make some of these relationships, time together. In fact, we need 4 more relationships. Okay, so let's look. Let's analyze. Actually, let's put one more point on here, which is going to be this point here, P. And again, it's going to be right there as well in the second state. So let's analyze B's velocity from P. And the reason we're doing that is because we know information about P. P has no velocity, right? Because it's not slipping with the ground, as we've done many times. Okay, so let's go B from P. So the velocity of B is the velocity of P plus the rotational term, or this is really the relative velocity that we write, because they're rigid bodies in rotation. They're just rotational, a relative, well, it's due to the rotation, but the relative velocity, right? Okay, this is why we chose to go from P, because it's no slip, and that term is 0. Okay, and then we have, this is the omega of B, k hat, crossed into the radius of the disk, j hat. All right, and that's from P. How do we get up to B? Is purely in the j hat direction, a radius of the disk, which is 200 millimeters. but let's keep it general for now, so we're not dealing with those numbers. And then k crossed into j is minus I hat. So this is minus omega b r disk I hat. Okay, that has a relationship between VB and omega b. So that's one relationship. Remember, we had 5 unknowns with only one equation here. We now have 2 equations to relate those 5 unknowns. Okay, now next we're going to do is, now that we know what VB is, at least in terms of omega b, can we relate it to the movement of A, the velocity of A? So let's analyze the motion of A from B, because these are both on the same rigid body, right? The pin, those are both part of the slender bar. So the velocity of A is the velocity of B that we now know. It's not 0, but we know it. Is the omega of the bar, right? That's the rigid body that connects A and B, crossed into the relative position of A from B, which is okay. Actually, that's the case. So we have VA. We're imposing that this can only move in the vertical direction, right? Slider can only go up and down along that chute. So our velocity of A is only in the j hat direction. This equals minus omega b r disk j hat or I hat plus omega bar that rotates in the in the plane, because it's a planar motion. So k hat crossed into, now this is minus L I hat. Okay, so what we're analyzing here is only state 2. Because that's where we, all this kinetic energy terms is at state 2. So this is at 2, where theta equals 0 degrees. At that one, then to go from B to A is minus L in the I hat direction. Okay, so from here on, now, or anytime we use this relationship, everything I think before now, like this was valid always. This one here. This one now is only going to be valid because we've imposed at state 2 right there. Okay, so let's see. Let's take the I hat component of this equation, and that's because 0 on the left, there's no I hat component, and the only I hat component, well, k hat cross I hat is going to be a j hat, so this is just minus omega b r disk. Well, the radius of the disk is a geometry that's not 0, definitely. So the only option there is omega b equals 0. Okay, before we talk more about that, let's go to the j hat component and see if we can get any more information, because that seems like something important to talk about. Here we have VA on the left hand side. VA equals oh wait, but actually, well, yeah, we'll come back to this. Okay, so VA is then going to be what's going to be related to omega bar times L, but is it minus or positive? So we have k crossed into I, that is positive j hat, but there's a negative in there, so it's minus omega bar L, and that's going to be important. Okay, so now this relationship, omega b equaling 0, we can actually use to tell us what VB is as well. Well, if omega b is 0, then VB is also 0. And this is what I was saying, what we could have just imposed from the get-go. That this makes, sense, passes the common sense test. Why is it? Well, because what I said before, right? We have the translational velocity of the center of mass of the disk together with its rotation. We're at the point where this started like this, swung out to there, look at my pen tip, and now it's going back. So right at this point, there's no velocity there, right? It's kind of held in, I should try to make sure this is sliding down. Sliding down, or right when we get to there, there's, like, how do you do this? It'd be like sliding out, and right there, there would be no motion, right? I think you can kind of visualize it, right? It's like a transition from rolling rolling this way to then, as this slides down, it's going to roll in the opposite direction, while that's rolling that, you know, the translation is that way to now this way. And so we're at that transition point where the velocity is purely zero, and therefore the angular velocity is purely zero. All right, so that allows us to come back up here and basically throw out this whole bottom thing. It simplifies the equation a bunch. And we also have what VA is in terms of omega bar. So at this point, we now have one equation up here for three unknowns, which is VA, VB, and omega, V bar and omega bar. And then we have one relationship down here which relates VA to omega bar. We only need one more relationship. And the one we're going to do is, what is the bar's mass center, the mass center of the bar from B? Just like we did A to B, we'll do the bar, and that should give us one more relationship. Okay, and I need another page for this. So let's now analyze, still in kinematics, what the bar center is doing from, and this is the mass center of bar, from B. So we have and these are on the same, you know, rigid body, which is the bar itself. The velocity of the bar is the velocity at B. And now we know that this is equal to 0, right? Isn't that great? Right? Before we actually had to plug that in, but now we know it's 0. Plus omega bar. And that's why this is going to be useful information, right? Crossed into the radius, the position vector of the bar with respect to B. Okay, so this is omega bar k hat crossed into, now this is minus L over 2 I hat, again at state 2 only. All right, to go from here to the center of mass of the bar, you have to go half of the length of the bar in the minus I hat direction from B there. Okay, and so from this we know that our velocity of the bar is, well, k cross I hat is positive j hat, but there's a negative in there, so we've got a minus L omega bar over 2, and that's it, right? So now we have one relationship here, one relationship here, and the big relationship here, where we now know we can determine everything. We do need to do some geometry to find these guys, but once we have it, right, it's just going to be plugging all the relationships in. And yeah, there's a little bit of algebra ahead of us, but we now know we can do it, right? So geometry, let's do the heights now. Okay, and these are just the initial heights. So it was initially at 60 degrees, where I'm determining YA1, and from datum, this is a hypotenuse of 1 meter. Okay, and YA1 is the height there. So this is just 1, and so therefore YA1 equals sine of 60 degrees times 1 meter, which is root 3 over 2 meters. Okay, now you could also go into this exact same triangle, because this is A and this is B. Well, the bar's center of mass is right there, and that is also the same triangle here, but this triangle now is 0.5, and this is Y bar 1. I should have, let me just go like this. Y bar 1 is that leg of the triangle, that leg of that inner triangle there. Okay, so we have Y bar 1 is now going to be a half, because the hypotenuse there is a half, times sine of 60 degrees. Well, that's just root 3 over 4 meters. Okay, we'll also need the moment of inertia. That's another geometrical property, right? That is in our equation that I just kind of overlooked. The moment of inertia of the bar, and we would also need it for this circular disc, but we already determined that this whole term is 0, so we really only need it for the bar. Okay, moment of inertia, I bar is now this is about its center of mass, so this is m bar. Okay, so this is going to be about its center of mass, is the mass of the bar, L squared over 12, slender bar. Okay, and now we just plug this into our work energy, everything we have. Plug a bunch of stuff in to the work energy relationship, and this is where, well, we'll just write everything down, right? We have expressions for y, the y values here, so we can just have m a g y a1 plus m bar g y bar 1 equals 1/2 mass of A. Now instead of, okay, this is what it used to be. Instead of VA, we now know that the velocity of A is omega bar L. So this is VA squared, so that'll just be omega bar squared L squared. Omega bar squared L squared. Let's see, the next term, might as well just keep this. Remember, these two terms are 0 down here. So we have the velocity of the bar. Well, we determined earlier here that the velocity of the bar is minus L omega bar over 2. So the term was 1/2. So it's a translational kinetic energy term, 1/2 mv squared for the bar. So this is 1/2 mass of the bar. And now we got velocity squared. Well, velocity squared is L omega bar squared over 2. So we got L squared omega bar squared over 4. And the last term is the rotational kinetic energy, 1/2 I bar omega bar squared. That one we're just plugging in what I bar is there. Okay. So we have plus 1/2 I bar is m bar L squared over 12 omega bar squared, and somehow we fit it into one line, which did not think was going to happen. Okay, so this left-hand term, we'll do some calculations once it's time, but let's see if we can combine all these. All of these terms have a 1/2. All of these terms have a omega bar squared. All of these terms have an L squared. What's left over? Well, we have a mass A. Right, we already took a 1/2 out of here. What else do we need to take out of here? These are both of these terms have an m bar in them, but here, let's do this separately. That means that once we have, in terms of, okay, 1/2 m bar L squared omega bar squared. All that's left over after this term is 1/4, and then 1/2 m bar L squared omega bar squared. All that's left here is a 1/12. Okay, well, the 1/2 is already pulled out. So this is actually 3/12 plus 1/12, 4/12, which is 1/3. So m bar over 3. All right. And remember, all we're doing is we're looking to solve for omega bar there. And at this point, we could actually do it as like an analytic expression. Omega bar equals 2. When we multiply the 2, both of those have a g, 2g, and then we have ma_ya1 plus m bar y bar 1. Okay, that's with just the 2 pulled over to the left-hand side. We're going to do a square root here in a second. Then we got to divide by L squared, and then that term, mass of A plus 1/3 mass of the bar. And square root the whole thing. All right. Looking good. Now we just plug things in, right? Is there anything tricky here? 9.81 meter per second squared. That's 2 kilograms. That we determined to be root 3 over 2. That's 4 kilograms. That we determined to be root 3 over 4. 1 meter for the length. 2 kilograms, 1/3 times 4 kilograms. This is not tricky, square root. All right, I always look, if there's something tricky, I'll put the numbers in. But here we're just plugging in now what we know or what we had earlier in the problem. So the angular velocity of the bar is 4.5155 radian per second. Okay, and that wraps up our examples and our discussion of the work energy. The next step is then, still in chapter 19, we'll be talking about momentum of rigid bodies and extending our analysis to the objects or rigid bodies can be in contact through collisions and impacts.